RNNs are hard to train. Why? The vanishing gradient problem. The case of the vanishing gradient. What's vanishing? The error signal. The blame. See, to adjust the weights, you need a gradient, a number that tells you how much to change them. But when you backpropagate through time, you're multiplying that number by the weights at every single step. Okay. And what happens if you take a number less than 1, say 0.5, and you keep multiplying it by itself? It gets smaller and smaller. 0.25, 0.125. Right, now imagine a sentence that's 20 words long. You're doing that multiplication 20 times. Yeah. By the end, the number is so tiny, it's basically 0. So the signal, it just vanishes. It evaporates into nothing. The network at the beginning of the sentence never gets the message that it made a mistake, so its weights don't update. It just stops learning from anything that happened in the distant past. Which means the RNN can learn short-term things like awesome sauce, but if it's a long, complex sentence, it fails. It can't learn what are called long-range dependencies. The pilot, who had flown planes for 20 years and loved the clear blue sky, suddenly crashed. The RNN's crashed. But by the time the error signal gets back to the beginning, it's so weak it has forgotten who the subject was. It might think the sky crashed. It becomes a goldfish again. That's a massive, massive problem. It is. Exploding gradients, which is the opposite problem. The numbers get huge and the whole thing crashes. But vanishing is the one that really held the field back for years. So how did we beat the villain? This is where the lecture shifts to a whole new architecture, right? The LSTM, the Long Short-Term Memory Network, which is a bit of a confusing name, but I get the point. A memory that can be both short and long. It's the elegant solution to the vanishing gradient.